Hey there, science fans! Today we're diving into the fascinating world of chemistry. Let's start with something we all relate to: recipes. Just like a recipe tells us how much of each ingredient to use, a chemical formula tells us the types and quantities of atoms in a molecule. Think about water, good old H2O. That formula tells us a water molecule has 2 hydrogen atoms, H2, and 1 oxygen atom, O. Now each atom has a weight, like ingredients on a kitchen scale. We call this atomic mass. To get the formula weight, we simply add up the atomic masses of all the atoms in the formula. For water, it's like adding the weight of 2 hydrogen atoms plus 1 oxygen atom. It's that simple. Formula weight helps us understand the composition of molecules. It tells us the relative weights of different atoms within a molecule. And that knowledge is crucial for many chemical calculations. Now, imagine trying to bake a cake using just a few grains of flour and sugar. Tough, right? Chemists face a similar problem. Atoms are so tiny that dealing with just a few is impractical. That's where the mole comes in. No, not the furry creature. In chemistry, a mole is like a chemist's dozen. It's a massive number, 6.022 times 10 to the 23rd to be precise, that represents a specific quantity of atoms or molecules. Just like a dozen eggs is 12 eggs, a mole of any element has a mass equal to its atomic weight in grams. This mass is called the molar mass. For example, 1 mole of carbon weighs 12 grams. Molar mass is super useful because it lets chemists measure out substances in a way that ensures they have the right number of atoms or molecules for reactions. It's like having a special measuring cup for chemistry. You might think that all atoms of an element are identical, but here's a surprise. They aren't. While all atoms of an element have the same number of protons, their atomic number, they can have different numbers of neutrons. These variations are called isotopes. Isotopes are like siblings in a family. They share the same surname, atomic number, but have different first names, number of neutrons. This difference in neutron count gives isotopes slightly different masses. For example, carbon has 2 stable isotopes, carbon-12 and carbon-14. Both have 6 protons, but carbon-12 has 6 neutrons, while carbon-14 has 8 neutrons. This makes carbon-14 slightly heavier. Isotopes are important in many fields including medicine, archaeology, and geology. For example, carbon-14 dating helps determine the age of ancient artifacts. Now, how do scientists identify and study these isotopes? Enter mass spectrometry, a powerful technique that acts like a fingerprint scanner for atoms and molecules. Imagine a crowded room, and you want to identify everyone based on their weight. Mass spectrometry does something similar. It separates ions, charged atoms or molecules, based on their mass-to-charge ratio. In a mass spectrometer, a sample is vaporized and ionized. The ions are then accelerated through an electric field and deflected by a magnetic field. Lighter ions get deflected more than heavier ones, creating a spectrum that reveals the different masses present. This spectrum is like a fingerprint unique to the sample. By analyzing the peaks in the spectrum, scientists can identify the different isotopes present and their relative abundances. It's a remarkable tool for understanding the composition of matter. Section 5. Molecular versus empirical formulas, chemical shorthand. Chemists are always looking for ways to simplify things, and chemical formulas are no exception. We have 2 main types: molecular formulas and empirical formulas. Think of them as different levels of detail. The molecular formula tells you the exact number of each type of atom in a molecule. It's like a complete ingredient list for a recipe. For example, the molecular formula for glucose is C6H12O6, indicating 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The empirical formula, on the other hand, gives the simplest whole number ratio of atoms in a compound. It's like simplifying a recipe. The empirical formula for glucose is CH2O, which means for every carbon atom there are 2 hydrogen atoms and 1 oxygen atom. Both formulas are useful in different contexts. The molecular formula provides the complete picture, while the empirical formula highlights the relative proportions of elements. Section 6. Separating mixtures like sorting candy. In the real world, most substances exist as mixtures, not pure compounds. Think of salt water. It's a mixture of water and salt. Chemists often need to separate these mixtures into their components, and they have several clever techniques up their sleeves. One common method is filtration, which works like using a strainer. If you have sand mixed with water, pouring it through a filter paper will trap the sand and let the water pass through. Another technique is distillation, which exploits differences in boiling points. If you heat salt water, the water will boil and evaporate before the salt. By collecting and condensing the vapor, you can obtain pure water. Other methods include chromatography, which separates components based on their affinity to a stationary phase, and centrifugation, which uses centrifugal force to separate components based on density. It's like having a whole toolkit for sorting out the chemical world. Section 7. Atomic structure, a peek inside the atom. Atoms are incredibly tiny, but don't let their size fool you, they are bustling with activity. At the heart of every atom lies the nucleus, a tiny, dense region that contains protons and neutrons. Protons are positively charged particles, while neutrons have no charge. These particles give the atom its mass. Whizzing around the nucleus are electrons, negatively charged particles that are much lighter than protons and neutrons. Electrons don't just zip around randomly, they occupy specific energy levels called electron shells. Imagine these shells like orbits around the nucleus. The arrangement of electrons in these shells determines the atom's chemical properties. The outermost shell is particularly important, as it contains the valence electrons, which are involved in chemical bonding. Atoms strive to have a full outermost shell, and they achieve this by sharing or transferring electrons with other atoms, forming chemical bonds. Section 8. Effective nuclear charge, the pull of the nucleus. Imagine the nucleus as the sun and the electrons as planets orbiting it. The nucleus exerts an attractive force on the electrons, keeping them in orbit. This force is called the effective nuclear charge. However, the inner electrons can shield the outer electrons from the full pull of the nucleus. Think of it like the inner planets blocking some of the sun's gravity from reaching the outer planets. The effective nuclear charge experienced by the outermost electrons influences an atom's size and its tendency to attract electrons from other atoms, its electronegativity. Atoms with a higher effective nuclear charge tend to be smaller and more electronegative. Understanding effective nuclear charge helps explain trends in the periodic table, such as why atomic size decreases from left to right across a period and increases from top to bottom within a group. It's all about the balance of forces within the atom. Section 9. Magnetism in atoms, tiny magnets in action. Did you know that atoms can behave like tiny magnets? It all boils down to the behavior of electrons. Electrons not only orbit the nucleus but also spin on their axis like tiny tops. This spinning motion creates a magnetic dipole moment. In most atoms, electrons are paired up in their orbitals, with one spinning up and the other spinning down. Their magnetic moments cancel each other out, resulting in no net magnetic field. However, in some atoms, like iron, there are unpaired electrons in their outermost orbitals. These unpaired electrons create a net magnetic moment, making the atom magnetic. This atomic magnetism is responsible for the magnetic properties of materials. Materials with unpaired electrons can be attracted to magnets, while materials with all paired electrons are not. It's a fascinating example of how the behavior of tiny particles can have macroscopic effects.